So it's over. I'm getting we keep going to that. We never do.
We need to.
We always say, yeah, let's get to that section. Everybody walks out like, see you Wednesday. Like, can you like establish a date? I have a break all the time. On Tuesdays, I only have one. Thursdays, I only have one. So I'm gonna have to laugh.
Okay, homework. Okay, today is gonna today I feel like every day has been we keep trying to overview, really understand the big picture of what's going on, and then we add a little bit more every day, a little bit more of the nuts and bolts, but we keep trying to overview everything. So if class is not kind of like resolving your homework questions, so obviously we're not spending a lot of time going over homework problems. If what we're doing in class is not resolving your questions that you're having when you're doing the homework, then come to office hours. I'm getting 0 customers in office hours, and so that I just leave that up to you. If there's things in the homework that you're not sure about, and class isn't kind of taking care of that for you, that's on your initiative then to come into office hours and let's have these discussions that we need to have to improve your thinking about things and resolve your issues. Okay, so please come to office hours. I welcome it, okay? And also, don't forget the videos, right? Post on Blackboard. I get them up the afternoon of class. It's really helpful to go back and listen and find all those things that, when you hear something the first time, it's not going to stick forever. It could make sense when you're walking out the door, but then 3 hours later, it starts to get hazy, and then 12 hours later, it's maybe half gone, and then 24 hours later, anything that was new, right, is gone. So this is what the videos are for. So repetition is how things start to get solidified.
They help a lot.
Okay, good. Yeah, so take advantage of the videos. Okay. What calculus is about? 2 fundamental problems. You know how much of something there is, and you want to know how fast it's changing. And you know how fast something's changing, and you want to know how much of it there is. Our journey so far has been number 1 or number 2? Number 2. We're working on, we have the information about how fast something is changing, and we want to know how much of it there is. And that's called integral calculus. Okay, so we have started our first month of the course developing this thing called integral calculus, right? And everything we've done has been important to build to this very important idea in calculus. Okay? So we know how fast something is changing. We want to know how much of it there is. So how is it that we're representing how fast something is changing? What do we start with? How do we represent? What's that? Ad and I just said a rate function. Is that how we represent this thing of how fast something's changing? Agree with that? Yeah. That's our rate of change function, right? And we want to know how much of it there is. What about that? Accumulation, right? Okay, so how do we get there? So we have our rate of change function. What was the first thing that we're going to do in getting an accumulation function from a rate function? What's the first thing? Okay, Corey said a step function. Is that what you were thinking? We should all have been thinking that. Right? So yeah, so how do we get there? First thing, the constant rate of change step function, right? And from the constant rate of change step function, what do we do with that to move towards accumulation? Why? How do we use that? What do we do? It goes to the idea of what accumulation is. Summation of?
Of all the rates of change during specific intervals.
Okay, so summation of all the rates of change. Are we summing up the rates of change? Oh, go ahead. You want to change it?
The changes in y with different rates of change.
Okay, summing. She changed it to summing up changes in y. Because accumulation is things accumulate little bit by bit, and so with a constant rate of change step function, we can calculate these little bits of change, right? And then we can sum them up. Okay, so this is the kind of the big picture of what we've been doing. Hugely important to understand everything from the big picture all the way down to the nuts and bolts and everything in between, okay? So, but we're always keeping the big picture in mind. So as you're working on a problem or you're doing something intricate or complex, always ask yourself, where does it fit into the big picture? Where does it fit into the big picture? Okay, another way to look at it. Our rate of change function, we made the step function. We made that from, we use as our convention, left. R of left of x was our step function. And then on Wednesday, we built up the accumulation function, okay? Had you seen this on the first day of class? You might have been a little scared, right? You might have even dropped, okay? It looks kind of scary, but we know what everything means, okay? So let's review the meaning of this. So in general, there's two parts. There's this part and this part. What about that first part on the left? What is that about? Somebody new? Yeah, Stanley.
It's the sum of all the changes in y over all the full intervals leading up to where your current x value is.
He said the sum of the changes in y for all the full intervals leading up to where your x is. What do you think about that? Agree? Couldn't have said it better myself, okay? It's the sum of the bits of change for all the full intervals between our starting point A and up to our roving value x, right? It's a function of where we end, right? So this is all the full intervals, okay? This part. Somebody from the back, so we got lots of good participation in the front. How about in the back? Yeah, Daniel.
The last partial interval.
What about the last partial interval?
It's the rate of change for that one up to the x that you mentioned.
So this is the rate of change.
Well, it's the rate of change multiplied by the amount of the interval,
Which gives you?
which gives you the accumulation of that.
Right, exactly. The last bit of change, right? The last little bit of accumulation for the partial interval. Okay, so that's helpful to know which each of the two pieces are. But really, in a very basic, but what is all of this? In a very basic sense, this accumulation function is, in the most simplest form, what is it? So, this is really something, so the idea of this is something very simple that we talked about.
Y equals, I forget,
Delta
T.
y.
Delta y equals k delta x. Okay, there's a little bit more to it, right? So it has to do with delta y equals k delta x.
Plus a little bit more.
And then B plus M times X minus A.
No, now you're off track. Now you're off track. Yeah, so what is this? This is just summing up. It's just summing up. What? What is it summing up? So the first part, where's R? That whole thing is just a rate, right? Same thing here. It's just a rate. And then we have delta x times delta x. And we're doing what to those? Rate times delta x. This means? And what function is this again? Our accumulation function. Accumulation is about? Tyler, what's that?
Adding up all the changes in y.
Adding up all the changes in y. And we can get those changes in y using the idea of constant rate of change. This is what, so when you see the accumulation function, yes, the details are important. You need to understand all the details. But you never lose sight of what it is. It's just summing up a bunch of changes because that's what accumulation is. Bit by bit, things accumulate bit by bit. So what do we use to get those bits of change? This is the idea of delta y equals, which is what? Constant rate of change, right? That's why we have the step function, so we could use constant rate of change. Okay, then we have so we have all the full intervals, r delta x, r delta x, r times delta x, and then we have the last partial interval. Yeah, so don't get lost in the minutia of all the symbols. Yes, you need to know what they mean on a micro level, but never lose sight of what this whole thing is doing on a macro level. It's just summing up a bunch of k delta x's, which is accumulation bit by bit, changes in y. Okay, so there was something in your homework that said, how if this was based on left, right, the left x, how could we adjust this so it's based on mid x? So let's start with the full intervals. How would we adjust that, the full interval part, so that it would be based on the mid x rates rather than the left x rates? So, do we need to change something about the rates, or do we need to change something about the interval width? So by using mid, does it change the interval width?
Well, so there it says left x, we're not taking.
No, we're talking about the full intervals right now. What do we need to change when we sum up the full intervals if we want to use mid rather than left?
How many delta x's you're adding to the...
How many delta x's you're adding?
That's the whole thing.
So this is, what is this? This is the x value that's getting us the left value of x in the rate. So we built that yesterday. This is the x value at the left end of the interval, right? He wants to add a half a delta x to that. And that will give us the x value at the midpoint, and then we'll get the rate at the midpoint. That's it. See, that input into the rate function is the x value at the left end of the interval, or every left end. So now if we want to get the rate at the midpoint to be our constant rate, we need just to move over half an interval further. That's the new x value, and so then we'll get the rate at the midpoint. So if we added delta x over 2 to that, that would get, yeah, Stanley.
But if you just took, I understand why that works.
Okay.
But if you did j minus 0.5, would that get you the same
J
thing?
minus 0.5.
Instead of 1. So it would be half.
Yeah, so if we do the math here, so j times delta x minus delta x, that's what we have, right? If I multiply that out, plus delta x over 2 would just be j delta x, what now, minus delta x over 2, and so you're saying j minus 1/2. Sure. That's another way to think of it. So here's the old way, and then here's the mid, so I just can combine those to minus and then factor out the delta x, and so then the j minus 1 becomes j minus 1/2. Yeah, that's another way to do it. It's good. Okay, what about over here? What do we need to change here so that it's using in that last partial interval, rather than using the rate at the left side, it's using the rate at the mid. So what do we need to change?
Change left to mid.
So change left to mid. Here?
Yes.
Both of them?
Just the first one.
Okay, some people are saying both. Some people are saying just the first. Are we in agreement that we're going to change this one? Yeah, we want to get the rate at the midpoint of the interval. Okay, so then remember what this is doing. What is this x minus left x doing? So we got, here's our intervals. So say our x value is right here. Boom. There's x. What is this about right there? Do we want to switch it to x minus mid? Amos, why not?
Because it's just telling us how far we're going past it. Well,
So
it's that maybe right there.
what is this? Yeah. So this is left x. So x minus left x is this distance right here.
And we don't want it to be half of that distance. We have to change it.
Yeah, exactly. So we add up all the little changes for the full intervals, and then we want the change associated with that distance right there, which will remain x minus left x. If we do x minus mid, we're going to get a distance like, for this particular case, we'll get a distance like this. Is that how we want to multiply the rate by? No, we want to multiply the rate by this distance from the last left end out to our final value of x. So that's what we need to do. We need to change this to delta x over 2, or change the 1 to 1/2, and then get our rate on the last little interval to be from the midpoint. But we leave this as it is, because it's going to be that thing right there. Okay. So any questions on the big picture or the little picture of the accumulation function that we built Wednesday? So this is we've been working on this for like 3 weeks now. To come up, given a rate function, come up with accumulation function. You what, if you want to do it on the right end?
I mean, are we going to need to know how?
You should. Yeah. So that's a nice problem to think about. Yeah. Yeah. After that, so I think you can all do it after talking about it. Other questions? Okay. So I have okay. So you should have this this file that we started Wednesday built in Graphing Calculator. If you don't try to type this in now. Okay, it's gonna take too long, and you'll not be able to pay attention. So if you've got it, you can open up and use it. If you don't have it, listen. Don't try to type it in now. Okay, thanks. Oh, can I have one? Mark. Next. Okay, so we said this is what we've been working on. To have, if we could write command lines to have Graphing Calculator do the work for us. If we understand it, then we can have Graphing Calculator do all the tedious stuff that would normally be tedious that we'd be doing by hand. We can have it do that all for us. But the requirement is that we really understand what we're doing. Okay? So I've got a rate function here. Okay, and this rate function represents the rate of change of the weight of an object, okay, over time. So this is time going by, and this is the rate of change of the weight of an object. Maybe it's some amount of a substance that's falling off a truck, okay? So there's our rate function, and then the next command line, y equals rx, that graphs it. I'm graphing it in red. and then we've got our changeable delta x value. What did this next line do? So this right here, this line here, a plus cx 0 for c from 0 to 400. Remember what that did?
Points.
What did that do for us?
Oh, it just allowed us to plug all those points in the interval.
If I turn this on, what will we see? What is it?
The dots
What dots?
on the x-axis.
Yeah, it's marking off the intervals on the x-axis. So we did those in red. Okay, so it puts those dots in there. So that helped us to understand building the step function, but now that we have it, we don't really need to see those anymore. But it did definitely help us. So I'll leave them on there. Okay, then we built our left function. You should be really confident, especially for your quiz today. It's all about left, mid, right, and how we use those with R to build a step function. Okay, so the left function, what's the input into the left function? What kind of thing is the input? X. And what's the output of the left function? Just any x? Yeah, so you're going to input an x, say right here, if I input this x of 1.8, left x is going to spit out 1.5. If I put in x of 1.6, left x is going to spit out 1.5. So every single x value right in there, that function is going to return the x value of 1.5. Why? Why do we want that? Why do we want all those x values mapping to the value of 1.5?
That's what we're returning as a root. The delta is smaller than that point, so we want all of them
We want all those x values to have
the same rate of change.
the same rate of change as that one. So we take the outputs of the left, right, and we put them into the rate function, and that'll give us our step function, right? And so then, and we did that Monday. And we got our step function here. I've got delta x set at 0.5, as we can see by the dots. Okay, then Wednesday, we build up this bad boy, right? And we've talked about it. Make sure you understand it from the big picture down to the details. So now this next step here, using apostrophes in graphing calculator is the signal to start a new graph on the right. Some of you have calculus before, and it might look to you like y prime, which is a really important idea in calculus. In graphing calculator, that apostrophe has nothing to do with that. It's nothing to do with derivative or prime. It's just the way, it's the method which graphing calculator uses as a command line to say, graph me a new graph. So this is telling you to take this accumulation function, and we're going to graph it over here in a new graph over to the right. So when I turn this on, what are we going to see? In general, so I'm not talking about will it go up or down or be negative or positive, but the general type of function that we're going to have. What will that be? We should all know that. Okay, accumulation, but what will the structure or format or what will it be like? What's that?
Linear.
Okay, she said linear. We're going to get a line. Linear piecewise. Is it linear piecewise, or something else? What does the accumulation function do?
It's gonna plot a lot of points, but they're gonna look connected by a line.
Okay. How about in the back? This Daniel, what do you think it's going to look like? One straight line? Okay, so we got one straight line. Sharon, what do you think? Yeah, no, yeah, Sharon.
So, this one is like it would be a bunch of lines, a different line for each interval, and then each line would have a different rate of change.
Bunch of lines for each interval, and each line will have a different rate of change. Like that? Yeah, that's what she said, right? Yeah, so this is our piecewise linear based on the constant rates on the step function. This is what the thing we did Wednesday. So remember before we did it by actually making a whole, each one separately, right? And we listed them. We did the first one, then the second one, then the third one, right? So now we've just come up with a way to do it in one line, rather than having the first line and then the second line and the third line and the fourth line. We've got now one function that does it all. Yeah.
But in graphic calculator, you have to have all of those different lines in order for it to plug everything into it. Like you have to have left of x defined where you can.
Absolutely. Graphic calculator is really stupid. It just follows our instructions. It doesn't have any intelligence. Yeah. We have to tell it what to do. Yep. The intelligence is on us. Okay? We have to give it the right instructions. Okay, so there's our mid and right. So I have a dynamic version of this. So again, this is a rate function for some object or some maybe pile of sand in a truck or something. And this is showing the rate of change of weight. Okay? So I'll run this. And you have your questions on the back side of that. If you flip it over, you see 7 reflection questions. And so we're taking all this work we've done and we're tying it all together with these questions, right? So this should really help to make everything make sense. Go slow. Get a partner or a group of 3. Talk through all 7 reflection questions, and I can come around and answer questions or have little discussions with you, okay? So work on these for about 10 minutes, okay? So get a partner. If your desk is far away from your partner, move your desk toward your partner.
Yeah, because it depends on. It's exactly the same point because like this is we're taking out to the left. We're estimating that the rate of change is the same for that function all the way to the next. It skips out the first. So say that we wanted 7 on there. That's estimated.
Well, mine is graph because that's what all
Yeah, for this one,
green lines are.
That's the big change in 3 million times. Okay? Okay, so the red one would be exact. So in the dynamic view here, what's being represented in this dynamic view? No, so You said it could be both.
Depending on how you look at it.
Right, okay, so but this is a dynamic view of it, right? For decreasing x. Which of those two is this showing?
X prime.
It's showing an estimate.
You're right, they're both there.
Yeah.
But,
But that was a copy of what was going on.
right, so this black, right, the black line with the dot,
It's following. Okay.
right, is treating that.
Okay.
Like in this was an estimation because it's based off of this stuff.
It's following the blue, not on the red. It's not. When I put blue,
I keep changing.
just make sure that you take what blue is. Because I put blue as the estimated time, the guesstimated rate of change that we use. So try to do it.
Oh, because that's how we estimate. Yes, that's
You know,
how we
that we're going to make that.
estimate.
It helps in part. Someone's not just
If we have the exact rate of change for that blue, it'd be different. So
Oh,
it makes it a lot
no, this
easier.
isn't asking us.
Is there any extra? Yeah,
Add every single point.
sorry? Is there any extra?
Estimating.
I was actually at all. It wasn't in the first part. It was that. No, it's saying how fast is the weight changing in the current value of time. So it's saying before you create a step change.
Okay.
So it's exact. That's just
Writing your
That's the right graph.
then create, and then now we're looking at
It's
only an estimation.
Can you slow down? Right So now this gives estimates now.
So basically, it's a question. It gives us estimates because that's what it's working
This example is like
I think so.
look at the points on the left graph, how fast the weight is increasing. But I mean, like the right graph is like where
That's the rate weight change. That's what I saw.
So point on the graph.
Estimated accumulated.
So if the one on the left knows this function, right? Totally separate function. So don't worry about it right now.
fast weight is increasing at
Q of X. So you said rate, rate, yeah, the rate. Rate of change.
regarding the weight as it's changing over time.
It's rate of change of weight.
Yeah.
So maybe it's like the weight on the ground as you're dumping something off the truck. So the weight on that material.
How fast?
That's the rate on it. It's the rate. The rate.
Yes, they need to do a bunch of.
Oh, that's all.
Yeah, this is the accumulation of all the points in that time.
Or it's the amount of
Divided the accumulation. Don't worry about a rate chart. Each of these,
all the total amount of weight is like.
What do you think? It's pretty cool.
That's how much weight is on the line.
I never got one as far as math.
Or not, or each piece of the
His idea
has a different. And like it's different.
Whatever that is.
Are you writing that?
Point on the right graph. Okay.
So maybe they can
What that function is that? Accumulation. So we let x go up to a certain amount, the y value is going to be. Yeah, if you say starting from A to X, your total change in y. The total accumulation of y.
I did something because the estimated rate of change changes.
Estimation. So we had a constant rate.
you define them there. Well, the point is to be looked at in a variable.
See, mine graph.
Point A is and 0, like 0.5 from point A to point C.
So let's not worry
You're
about
graphing the rate.
assuming constant rate.
Everybody else just like the rate. You graph the rate.
So I'm not doing how you design, what you'll find is
That graph.
You told them to graph the rate over here. You said you graph the rate.
Like it starts at one constant rate.
usually the questions
It
are.
changes like between like the points in that issue. And then the revenue function is
Oh, that's what it did.
Right, it's gonna be.
Mine is Christine.
One is going
Work on this for like that.
Estimated rates of change. You got an estimated rate of change. And then what happens?
It changes.
Boom. The rate of change changes.
Yeah.
No, just this part, just this B part.
Oh, okay, just the.
I wasn't really, I was fine with 40 lines and then I was like, I'm done.
and then you'll just like it.
Yeah, but if we know that there's no way that we live. Well, because just doing it first, we can answer every question.
I'm usually a super out.
Fair enough. So, yeah.
That's the actual amount of weight that.
So let's just talk about the point. What's the
First graph, the rate is always increasing because all of our funds But the second one is, I guess it's increasing 50%. Right?
No.
So
Wait, wouldn't it be increasing or decreasing rate? Like,
That's what I was asking.
wait.
That's what I was gonna ask.
Yeah. When it's saying, wait, increasing, wouldn't it be increasing? Increasing the time would decrease.
Since it's above, X, it's on top of X, the weight is still negative, so we can't say that. It's increasing. Yeah, 1 and 2, the rate at which it's changing is decreasing.
So how
So,
fast?
No matter what, so
Slowing down. It's still
so if I'm,
Or like,
so think about what it means for the rate of change function. That means that negative, it's decreasing right now. Okay, so we can still have a positive accumulation can still be positive, but actually, what's growing or decreasing, yeah. So then it is, it's increasing at a decreasing rate. So is that a proper way to write that? So maybe use it. Here's how I was how would you describe that to your mother or grandmother? I would say that. Well, I would tell her like, okay, so we're still getting bigger. Okay, so that's money. I'm still gonna give you money, but at a certain but not as much before. So we're accumulating and that's the hardest part is figuring out how to describe this in copies. I figured you guys can that you have a good handle on it. So this is for question multiplication.
Yeah.
So it's increasing at a slower rate over time.
In terms of money, it makes sense. It's so much, which is not as much. So you're still getting out there.
Okay, let's regroup. Okay, let's talk. Most of you got through most of the questions? Here we go. So, Savannah, where in this animation should you look to see elapsed time growing? Which one? Which x-axis? Left x-axis. Agree with that? What about this? Does this show elapsed time growing too? Yeah, both, right? So both x-axis, okay? Where should you look to see how fast the weight is changing for the current value of time? Anthony? Where in this animation should you look to see how fast the weight is changing at the current value of time?
Along the y-axis of both graphs.
Y-axis of both graphs is showing how fast the rate of the weight is changing. Jacob?
Only the right graph.
Only the right graph shows how fast the weight is changing. Connor? The left graph. We would know what these graphs mean, right? Where do you look to see how fast the weight is changing? Anthony?
It's the right graph.
The right graph. Lauren? We got to. We better get this right. You can't answer any other question. Go ahead. How fast the weight is changing, Beth?
It's technically in both graphs, but you look at the left graph on the step function, the blue lines, and then in the right graph, it's if you calculate the slope.
Okay, how fast the weight is changing is in the left graph. It's the y value of the left graph. This is the rate of change function. So it's telling us at a given time, the y-axis tells us how fast the weight is changing. Left graph. Okay? Is it estimated or an exact rate? So what the animation is showing, the animation is tracking on which? Estimated or exact?
Estimated.
Yeah, it's tracking on the estimate. It's tracking on the blue step graph. Now, the exact rate is shown in red. Okay? So both are shown, but the animation is tracking on the estimated rate. Okay? If we have the exact rate of change function, what's the purpose of creating the step rate function? Sure.
It makes it easier to calculate estimated accumulation
Yeah.
instead of having to add individual bits of change in x.
But even if we were, even any individual bit that we would add would have to be a step, right? Would have to be based on a constant rate. So it makes it, yeah, so we've talked about how it makes it easier. It makes it possible, okay? Better than, more than easier. It makes it possible to calculate accumulation using constant rate, okay?
So it allows us to use a constant rate of change. So it's the same thing.
Yeah, but what's the point of the constant rate of change? So that we can
On that.
calculate, what's it?
Whatever the point.
Bits of change. Bits of change, right? Okay, where should you look to see a of x, the accumulation function x? Kaiser? Right function is the accumulation. Does it give estimates or actual values of accumulation? It's this piecewise linear function, our accumulation function, is based on the step function, so they're estimates. These are estimates, or estimating function. Okay, what does a point on the left-hand graph represent? So we'll just come along here and stop it. Like that, please. Okay, a point on the left-hand graph represents a given time and an estimated rate of change. Rate of change of weight. Estimated rate of change of weight. What does a point on the right-hand graph represent?
The accumulation of all the points of delta y at to a certain point in time.
Yeah, so at a certain point, it's the y value is the accumulation of weight over that entire interval from 0 all the way up to the x value in question. Okay, why does the right-hand graph have abrupt changes in slope? Dan, what does that represent or show?
Well, because we're using constant rates of change, the weight is going to change at constant rate.
Yeah. Yep. So every time that constant rate suddenly changes, boom, changes, boom, changes, that rate is represented by slope on the accumulation graph, so it'll abruptly change wherever the rate. Okay, so between 1 and 2 seconds, is the weight increasing or decreasing? Between 1 and 2. Okay, how is that seen in the left graph? In the left graph, how do you see that the weight is increasing?
Because it's positive. Y positive, it's above the x-axis.
He's saying because the graph is positive above the x-axis, that shows us the weight is increasing. Agree?
Yes.
Yeah, that's right. How is it seen in the right graph that the weight is increasing? How do we see that in the right graph? David? Yeah, it's going up, right? So this is the accumulation of weight, and it's going up. It's going up between 1 and 2 seconds, between here and here. The accumulation is going up, so the weight's increasing, right? Over here, it's because the rate is positive. Because the rate is positive. Okay, so between 0.5 and 1.5 seconds, pause this. Between 0.5 and 1.5 seconds, how can from here to here, how can the change in weight from there to there be determined from the left-hand graph? So who knows what's going on? How can we determine the change in weight from the left-hand graph? Jacob, is that a hint? Oh, here. Talia.
You're going to take, so there's 2 different intervals.
2 different intervals.
So you're going to take the rate from each respective interval and multiply it by the distance of each interval.
Okay, so tell me what's right.
So for you write R2 delta x plus R3 delta.
This has been offered up. R2 delta x plus R3 delta x. Eric, agree with that? Does that get the change in weight from 0.5 to 1.5? Does that do it? Amos, what do you think? Yes? Zoo, does that get the change in weight from 0.5 to 1.5? Yeah, because this represents, what does this represent? Delta y, a little bit of change for that interval, plus the next little bit of change for that interval. Exactly right. Okay, what about the right-hand graph? How can we calculate that same thing on the right-hand graph? This, Daniel. How can we use the right-hand graph to get that same change in weight from 0.5 to 1.5? Any idea? Yeah.
Oh, you basically lock it out and you can add the area to the curve since we have nice constant rate.
Okay. No, it's not. It's not area under the curve. Adelaide.
Don't you just add the
Add the slopes. what does a point on the right-hand graph represent? So at 1.5, what does that point represent? What's the x value and the y value? So you can't lose sight of this.
X value,
Time,
Y is amount.
and y is what amount? Be specific. Accumulated weight over the whole since 0. So maybe it's 3.9 or something. So that's time, and this is AX, which is the accumulated weight over that 1.5 seconds. All the accumulated weight over that 1.5 seconds. So how can we use this right-hand graph to get the change in weight from 0.5 to 1.5?
Wouldn't you just subtract the Y value at 1.5? Or the Y value of 0.5 from the Y value?
So tell me what it will be.
Y 3.9 minus.
How do we write the y value at 1.5? A of 1.5.
Minus A.
Is it right? Does it make sense? This is all the accumulated weight up till 1.5, whatever this is, seconds. This is all the accumulated weight up until 0.5. So would this difference give you the change in weight? Yeah, that's it. So we can look at it as summing up bit by bit, or difference of actual accumulated weights at those two different times. The difference will give us the change. Okay, if there's still things from homework that's not making sense, find one of us and come to office hours and let's talk about those things. Again, your quiz is mostly about left, right, and mid, and how we use those with the rate function to build the step function, and how we represent it graphically. Okay? Have a good weekend.
That's because this is fun.